Hello, friends. Welcome back. Today we are going to discuss a very important topic, that is what happens to rivers when a sewerage water mixes with it. You might have seen this sight very often near your home, that people actually throw their garbages and waste into a nalla, and that nalla, which is a sewerage, open sewerage system, that ends up in a river. And what actually happens in that river during its flow is kind of very shocking, and that we are trying to see today, theoretically as well as then mathematically as well. We are going to use some modeling equations to study the pollution of river. So please kindly like, share and subscribe to my channel, and definitely watch this video till the end, because in the end we are going to actually solve a real life situation and see how we can actually apply. So talking about the river pollution, let me just start it. Yeah. So talking about river pollution. So this is a depictive example of along the length of the river. This you can consider as the river is flowing in this direction, and at say this point, say a bad water or a nala water, or a sewerage water mixes with this river. So what happens, and what are the zones of pollution along the length of that river when it flows? So the first zone, when a sewerage is dumped into the river, the first zone, which is called a zone of degradation. So here the water is a bit turbid, dark, due to the settling of sludge on the bottom side, and in this is the zone where the dissolved oxygen, which is a very important quantity for a parameter to determine how fresh the water is, the dissolved oxygen level goes down to say 40% of the saturated, and there it ends the zone of degradation. Then comes the zone of active decomposition. This is the most polluted zone of river water flow when a sewerage is mixed. So here the conditions are mostly anaerobic. This means almost, there is no oxygen present here. You will see different gases such as H2S, CO2, methane. They will be coming out, and you might see some bubbles also in this region. And when this region is encountered, the dissolved oxygen of this particular region, it drops to 90%. This means there is no probability that a fish will actually survive in this region. And by the end, you can see it slightly improves. After this, it comes back to 40% again at the end of this region. But there is a point here which is also called as a critical point, where it actually drops to kind of a zero. This means there is no oxygen in this zone. This is called a zone of active decomposition. Then comes the zone of recovery. So here actually the recovery of the water starts, where the you can again see some algae growing here, because algae needs uh, some sunlight, or it needs some nutrients, and here you will see the water actually replenishing itself, and it again goes back to its original position in the zone of recovery. In first zone, generally, or in second zone, you will find that there is no living organism left, and maybe on some bottom side in first zone you might find some fungi or bacteria, which helps in degradation. So at the end of the third zone, which is the zone of recovery, the the water kind of the river kind of rejuvenates itself, and after this you can see a very clear water coming from this zone, and which is what we expect that the river should be, because we want to use river for various purposes. But the question is, how long is this path which a river has to take? How long is this path? Because after this path we are getting our normal river which we want, but not before this. So here we are kind of making the river as a dead water. So is there a equation or a mathematical form or a way of analysis to actually devise the impact of sewerages mixing with open rivers? This might be a very profound sight in villages, urban areas, even in some cities. So let's try to see how is there a method to. Let me introduce you with Streeter and Phelps equation. So you can see this equation here. This is called as the Streeter and Phelps equation. Let me tell you what it actually models. It models oxygen sag. Oxygen sag. Oxygen sag is the deficit of oxygen in the water. As we saw that the DO level falls, the dissolved oxygen falls. So deficit is the saturated DO minus actual DO. So say saturated DO at a given temperature is 8 milligram per liter, and the actual DO in that river water is say 6 milligram per liter. So the deficit dissolved oxygen is given by 2 milligram per liter. So that's what it models, and there are different values here. Let us try to understand what those are, and after this we are going to actually look at solving a small problem, a small river water problem. So dt, what is dt? Dt is a DO deficit in the stream after time t, after the water has traveled for certain time distance from the instant of pollution or at a distance x equal to ut. So u is the velocity at which the river water is flowing, and x is the distance traveled by that water, and t is the time taken. So we will see one by one what it means. L0, L0 is the initial BOD of the stream, that is at time t equal to 0. So before polluting, there is some BOD, that is biological oxygen demand, which is a measure of biological matter in the river water. If river water is very clear, it will be like 3 milligram to 4 milligram per liter of BOD in river water. If it is too much of polluted, it is in the region of 250 to 300 kind of uh, BOD we say. Then DO. DO is the initial deficit. Please remember that it is the initial deficit. This means the saturated DO minus actual DO. Then K is the BOD reaction rate constant, which is also called as deoxygenation constant per day. Per day is a unit which comes via after solving the rate equation for BOD. So organisms are eating the material, and while they do that, they consume oxygen, and that's why it is called as the deoxygenation constant. Now, interesting thing is the deoxygenation constant, this value K also takes care of the temperature. The reason here is when the temperature is low, that is at around 0 degrees Celsius, the DO, saturated DO, the maximum oxygen that can be dissolved is around 15 milligram per liter. But when the temperature goes to say 30 degrees Celsius, the capacity of the river water to retain oxygen reduces, and it comes down to around 7 to 8 kind of milligram per liter. So deoxygenation constant, this term also takes care of the temperature. Similarly, K2 is the DO deficit reduction rate, or you can say reoxygenation constant. So when river flows, due to the turbulence or due to the velocity, it gets mixes with the atmospheric air, and also if there is algae present in the water, the algae also produces some oxygen. So what is the reoxygenation constant? That it is given by K2. U is the mean velocity of the stream of the river, and T is equal to time of the day, and critical oxygen deficit. So what is the, as we saw in the in second zone, there was a point where the DO drops to the minimum. So what is the maximum value of the deficit here, because we are calculating in terms of deficit. So when DO will be minimum, the deficit will be the maximum. So D critical is given by this formula, and the time required to reach that the critical deficit is given by this formula. So this is the model of a situation where sewerage water actually mixes with the river water. So this is a river, and this is a sewerage water. So this is about the model. Remember the name, the Streeter and Phelps equation. Now we will see how actually we can apply this. Okay. So You can see it's a small diagram I have made to let you understand what happens in actual real life. So this is the river which is flowing in this direction. There is a sewerage which get mixes with the river at this point. And so I have given some color coding so that we can deduce the oxygen DO levels. So at this point you can see the DO is minimum. So now there is a sewerage. Let's solve this as a problem and try to understand how actually we can use a Streeter Phelps equation to calculate important things when we want to model a river pollution. So BOD of this sewerage is very high, that is 200 milligram per liter. And so this is a waste flowing from uh, a city side or urban side. So definitely the DO is very high. BOD is very high, and hence the DO is less, that is 1.5 milligram per liter. It is flowing at this rate, say 5000 liter per second, or you can also say 5 meter cube per second. Now, what are the parameters of river? So BOD of river is very small, that is 3 milligram per liter, which means it is a very healthy water, and very high DO 7 milligram per liter. It is flowing at 50 meter cube per second or 50,000 liters per second. The cross sectional area of the river bed is given, that is 200 square meter. Then deoxygenation coefficient is zero point 0.4 per day and reaeration coefficient K1 is zero point 0.2 per day. You can see that reaeration coefficient is actually less than deoxygenation coefficient. So this means the ability to reaerate itself, the ability of river to reaerate itself is less than the organisms which are eating away the oxygen, and that is the reason why we should not put any sewage into our flowing rivers. Now let's see how we can get to solve our two questions. So first question is, what is the DO level at 10-kilometer distance? So can we find that? That is the first question which we are trying to see here. And second is, what is the distance at which the DO is minimum? What is this point? As I said, that there is a point which comes where the whole river is anaerobic, and it's very difficult to for any living organisms to breathe there. Now, from the given information, we will find the BOD of the mixture. As we said that 50 meter cube, this is in meter cube, and 3 milligram per liter of BOD is in the river. So 50 into 3 plus 5. This is a sewerage quantity of Q. These are QR, and this is QS, and these are BOD. This we multiply 50 into 3 plus 5 into 200 upon 50 plus 5. So that gives us a BOD of initial BOD we got, that is L0. Now we have a DO of river water and DO of wastewater. And also remember that the saturation DO here is 8 milligram per liter. So 8 milligram per liter is the saturation DO here. So DO of a mixture is again calculated 50 into 7 plus 50 is again the quantity of water flowing per second into 7. 7 is the DO of river water, and plus DO of sewerage water, flow rate of sewerage water, which is 5 meter cube per second. Remember that these terms are given in meter cube per second and 1.5. So you get 6.5 milligram per liter. Now initial oxygen deficit, that is D0, is calculated by the saturated DO, which is 8 minus 6.5. We just calculated it here, so it is 1.5 milligram per liter. Then velocity of flow is calculated. So we have rate of flow, that is 50 plus 5, 50 meter cube plus 5 meter cube per second divided by 200, that is the area of cross section. So you get 0.275 meter per second. Now length of the flow is, this is our question actually, what is the DO, or what is the deficit of DO at 10 kilometer distance. So length of flow is 10 kilometer, which is 10,000 meters, and I am using this quantity here to find the time, that is T, which we will be inputting here. So time to cover that much of distance with a velocity of 0.275, which we just calculated, is 0.42 days. Remember that this unit is in 0.42 day. The reason is K and K2 values or K1 values. Here it is K2, but it is nothing but K1, which is reiteration coefficient, are in per day. That's the reason I am calculating time in day. Now we have all the required coefficients, all the required inputs to find the dt value. Now let's input this dt value here, and you will get some answer. So if you solve this, you will get this as 7.289. Remember, this is the deficit DO. So if you subtract 7.289 from 8, so you should get something around 0.711 maybe. So 0.711 is dissolved oxygen at 10 kilometers. See, it's very less. So I don't think so that any life will actually exist even on 10 kilometer. Now let us find out what is our next term, that is what is the distance at which the DO is minimum. Now this can be calculated by, as I said, uh, use this formula T critical, find the time, and once you have time you can find T critical into velocity. Now let me just write directly for you here. So critical time comes out to be 3.289 days, and if you multiply this by velocity by converting the meter per second into meter per day, maybe, because we want answer, we have our time in day here. So velocity, please convert, that is a kind of exercise for you. So you will get the answer, that is around 78.15 kilometers. So the point at which the DO drops to minimum is 78.25, 78.15 kilometer. Now just imagine this, that even at 10 kilometer distance there is hardly any DO, and we are talking about this region to exist over 78.15 kilometer. This means this 78.15 kilometers of the stretch of this river is almost dead, and this is something intriguing, and that's why I think this equation helps us in evaluating the impact of the sewerage water which we let go into the river. So I would expect that after watching this video, you will not throw any garbage or sewerage into open severages or nallas, because we want to save our river. And if you liked the content and if you think that it was helpful for the climate, please kindly like, share, and subscribe to my channel. Thank you very much.